Hello everyone, welcome to my channel. Please like and subscribe. In this video, we'll be learning how to design a cantilever retaining wall which is subjected with surcharge. In our problem, which states that a cantilever retaining wall as shown below is used to support a bank of this as shown below. This is the bank of this which is supported by the cantilever retaining wall. The top surface behind the wall is horizontal subjected to a dead load of surcharge of 14 kilonewton per meter square. The soil behind the wall is well drained with a unit soil of 18 kilonewton per meter cube. The coefficient of friction is such, and we have given the concrete strength of SAT and the concrete grade and the reinforcement grade of 460 Newton per millimeter square, and the diameter of main reinforcement is 12 millimeter, and the cover is assumed to be 40 millimeter. Now, in our problems, we are required to determine the maximum bending moment for the cantilever wall slab only, means that for the steam, this is steam. We are required to determine the maximum bending moment for this steam. This is steam, and this is soil, and this is heel strap of the retaining wall. Now, in your problem, you are required to determine the maximum bending moment of this steam on, and also we are required to determine the maximum shear force for the cantilever wall slab, means that for the steam on. Also, we are required to determine the main reinforcement required and to check for the shear reinforcements. Now, let's start step by step. Data given. Let's analyze first of all our data to be used for the design. Data given. We have given surcharge of 14 kilonewton per meter square. Also, we have given the unit weight of soil of 18 kilonewton per meter cube. The coefficient of internal friction is 30 degree, and concrete strength, which is FCU, is also 30 Newton per millimeter square, and reinforcement strength, which is FY, is 460 Newton per millimeter square. Also, we have given the concrete cover of 40 millimeter, and diameter of main reinforcement is 12 millimeter. Now, this is also have this steam thickness. The thickness of steam is 300 millimeters. The thickness of steam. As this retaining wall have a height, this retaining wall have a height from the ground level up to the base. It have distance of 4.5 meter, and the thickness of slab and the thickness of the base of this retaining wall is 0.275 meter. Now, to obtain the height, now we have given the height from the ground level, the height from the ground level up to the base is 4.5 meter, and the thickness of this is 0.275 meter. Now, to obtain the height of because this is steam, we are required to determine the maximum bending moment in the shear force for the steam owner. Now, to obtain the height of this steam owner from the base of the retaining wall up to the ground level, this is the height of steam, is obtained by taking 4.5 meters minus 0.275 meters. So when we minus here, it will be 4.5 minus 0.275. It will be equal to 4.225 meters. This is the height of steam one. That we are going to use it for the designing of this bending moment in shear force. Now, the next is to draw the pressure diagram. The pressure diagram for this cantilever retaining wall, which is subjected to surcharge. Now, let's start with the pressure diagram which is subjected to surcharge. Surcharge usually provides the pressure diagram with uniform lateral pressure, with uniform throughout the total height, uniform soil pressure. This is uniform soil pressure, means that it is constant from the ground level up to the base. Uniform soil pressure. This is pressure diagram which is subjected to surcharge. Also, the pressure diagram due to the soil pressure. This is the soil. Its pressure diagram is usually varies linearly, and pressure diagram this one, which is triangular in shape. So here there is horizontal force. This is horizontal force which acting horizontally. Horizontal force due to the soil, let's say force 1, and horizontal force due to surcharge. Let's say this is F2. And the distance from the base up to where horizontal force due to soil pressure acts, let's say, is usually taken as total height of the steam divided by 3. So it will be equal to h divided by 3. And the distance from the base to where the horizontal force due to surcharge this distance is taken by taking height of the steam divided by 2. And here this is the pressure due to surcharge, and this is the distance. This is the pressure due to active soil pressure. Pressure due to soil pressure, which is called active pressure. Now, first of all, let's determine the coefficient of active pressure. Coefficient of active pressure. Coefficient of active pressure is determined by taking 1 minus sine of internal angle of friction plus 1 plus sine of internal angle of friction. When we simplify this, it will be equal to tan squared theta times squared 45 minus angle of internal friction divided by 2. Now we have given as internal angle of friction, which is 30. So when we substitute, it will be equal to tan square 45 minus 30 divided by 2. This is 30 divided by 2. It will be equal to 1 over 3. After determining the value of coefficient of internal friction, the first question we were required to determine the maximum bending moment of the cantilever. Before determining the maximum bending moment of cantilever, let's start with determining the pressure due to soil. Pressure due to soil. Pressure due to soil. Pressure due to soil. This is active pressure. This active pressure is obtained by taking unit weight of soil times coefficient of active pressure times height of the steam. Now, when we compute this value, it will be equal to unit weight of soil is 18 kilonewton times 1 over 3 times h, which is 4.225. When we compute this, it will be equal to times 18, it will be equal to 25.35. This is kilonewton per meter square. This is active pressure due to the soil. 25.35 kilonewton per meter square. Next is determine this horizontal force due to soil. Horizontal force due to soil. Horizontal force due to soil. This is obtained by taking the area of this pressure diagram due to soil, which is triangle in shape. So the area of triangle is taken by taking a half times width, which is active pressure, times height, So when we substitute this value, it will be equal to half times 2.5, 25.35 times h, which is 4.225. Now horizontal force due to soil, it will be equal to 4.225. It will be equal to 53.55. This is kilonewton per meter. This is horizontal force due to soil. Now, next, let's determine the maximum bending moment due to soil. Maximum moment due to soil. Maximum moment due to soil. Let's say this is maximum moment 1. This maximum moment due to soil is obtained by taking this horizontal force times its perpendicular distance, which is F1 times h over 3. Now when we compute this, what will be equal to 53.55 times h, which is 4.225 divided by 3. Now maximum moment due to soil, it will be equal to times 4.225 divided by 3. It will be equal to 75.42. This is kilonewton meter per meter. Next is to determine the pressure due to surcharge. Pressure due to surcharge. After that, we will combine the maximum bending moment due to soil and the maximum moment due to surcharge, and will enable us to get the maximum moment for the steam wall. Now, let's find the pressure due to surcharge. Pressure due to surcharge. This is PQ. Because surcharge provides uniform lateral pressure, so its pressure it will be equal to coefficient of active pressure times surcharge. Pressure due to surcharge will be equal to coefficient of active pressure is 1 over 3 times surcharge. Surcharge is this one. 14. Now when we compute this value, 14 divided by 3, it will be equal to 4.67. Now surcharge, pressure due to surcharge, it will be equal to 4.67. This is kilonewton per meter square. After that, we're going to determine horizontal force due to surcharge. Let's say this is force 2. Horizontal force due to surcharge, which acts to this pressure diagram of surcharge. So this horizontal force normally is obtained by taking the area. The area caused by due to surcharge. This is triangular in shape. This is rectangular in shape. So its area is taken by taking this weight times h of the steam. So this area will be equal to weight, which is pressure due to surcharge, times h. So it will be equal to 4.67 times h, which is 4.225. Now horizontal force due to surcharge, when we compute this value, 4.67 times 4.225, it will be equal to 19.73. This is kilonewton per meter. Next is to determine the maximum moment due to surcharge. Maximum moment due to surcharge. This is maximum moment. This is maximum moment 2. Now maximum moment 2, it will be equal to horizontal force due to surcharge times perpendicular distance. Perpendicular distance is h over 2. So it will be equal to force 2 times h over 2. It will be equal to 19.73 times h, which is 4.225 divided by 2. 19.73 times 4.225 divided by 2. It will be equal to this maximum moment to it will be equal to 41.68. This is kilonewton meter per meter. This is maximum moment due to surcharge. Next is to determine the maximum moment of this system. This maximum moment of the steam is obtained by taking the maximum moment due to soil plus the maximum moment due to surcharge. So we take the maximum moment due to soil, which is maximum moment 1, plus maximum moment due to surcharge, which is maximum moment 2. Now maximum moment, it will be equal to maximum moment due to surcharge due to soil was 75.42 plus maximum moment due to surcharge, which was 41.68. When we plus this value, maximum moment due to surcharge 75.42 plus 41.68, it will be equal to 117.10. This is kilonewton meter per meter. This is the maximum moment that we are required to determine for the steam wall. Now, next step, which is B, we are required to determine the maximum shear force of this steam wall. Maximum shear force of this steam wall. Maximum shear force is obtained by taking the total horizontal force. The total horizontal forces for the soil and for horizontal force due to surcharge. So maximum shear force is obtained by taking force 1 plus force 2. Maximum shear force will be equal to horizontal force due to soil, which is force 1 was 53.55 plus horizontal force due to surcharge was 19.73. Now let's compute this value. 53.55 plus 19.73. It will be equal to 73.28. This is kilonewton per meter. This is maximum shear force. Maximum shear force required for the steam wall. 73.28. This is kilonewton per meter. Next is to determine the main reinforcement. Main reinforcement is determined by taking the area of steel reinforcement is equal to design moment over 0.87 FYZ. But how to determine this maximum design moment? Maximum design moment is obtained by taking maximum bending moment of the steam wall times factor of safety, which times factor of safety due to the factor of safety of the dead load weight due to the self weight of the structure. So maximum design moment will be equal to 1.4 due to the dead loads times maximum moment of the steam. So maximum design moment will be equal to 1.4 times 117.10. Maximum design moment, it will be equal to 1.4 times 117.1. It will be equal to 163.94. This is kilonewton meter per meter. This is the maximum design moment for this steam wall. Now, Let's determine the value of z. The value of z is obtained by using this formula. Effective depth bracket 0.5 plus 0.25 minus k over 0.9 and out. This should be less than 0.95 times effective depth. So let's find effective depth. Effective depth is obtained by taking the thickness of steel minus cover minus diameter divided by 2. Effective depth will be equal to the thickness of this system. The thickness of this system was 300. So 300 minus cover, which was 40, minus diameter, which is 12 divided by 2. So when we compute this value, 300 minus 40 minus 6 will be equal to 254 millimeters. This is effective depth. After that, let's determine the value of K. The value of K is obtained by taking maximum design moment over SU PD square, which is equal to maximum design moment, which is 163.94 exponent 6 over FCU. FCU was 30 times beads for the cantilever retaining wall B is taken as 1 meter, which is equal to 1,000. So we multiply by 1,000 times effective depth, which is 254 square. Now the value of K, it will be equal to 163.94 exponent 6 divided by 30 times 1,000 times 250 square. It will be equal to 0.0847. Now let's compute the value of Z. If we substitute this value into this formula, you'll be able to get the value of Z. Now let's divide by 0.9, 0.25 minus answer, under root of answer plus 0.5. It will be equal to 0.89 times effective depth. This is less than 0.95. So after that, we multiply by the value of Z. So it will be equal to 0.89 times 254. It will be equal to 0.89 times 254. It will be equal to 226 millimeter. This is the value of Z, 226 millimeter. After that, now let's substitute into the formula for area of main reinforcement so as to get the reinforcement required. So max area for main reinforcement taken by taking maximum design moment over 0.87 times FYZ. Now let's substitute its value. Maximum design moment, which was 163.94 exponent 6 over 0.87 times Fy, which is 460 times the value of Z, which is 226. Now the area of main reinforcement, when you compute this value, x-1 6 divided by 0.87 times 460 times 226, it will be equal to 181 This is millimeter square per meter. This is the area provided. Now let's use table so to determine the area required and spacing for that reinforcement. To obtain the area required, we take the maximum area which is close to this one, and after that we determine its spacing for that reinforcement required. Now our area is this one, 1813. So when we come to this table of value, the area which is closer, so it will be this one. It will be this one. It will be this one. It will be the length bars with a diameter of 20, which gives the area of 2090 at a spacing of 15 millimeters. So we say that provides tension, provide bars with a diameter of 20 at a spacing of 150 millimeters center to center, which gives the area which is greater, closer to this, which is 2090. This is less than the area provided. So the greater area closer to that area provided is this one. So it will be equal to 2090 millimeters square per meter. Now this is the area of main reinforcement required. Also, you may be asked to determine the distribution area required. Let's find the distribution area. Distribution steel reinforcement. Distribution steel reinforcement. The area of distribution steel reinforcement. This area is obtained by taking the minimum area required. The minimum area, which is given by this formula, 0.13% times width times effect times thickness of steam. Now, minimum area, which it will be equal to 0.0013 times width, which is 1000 times the thickness of steam was 300. So the minimum area, it will be equal to 0.0013 times 1000 times 300. It will be equal to 390 millimeters square per meter. This is distribution steel reinforcement. Now let's determine its area required for this area and its spacing for that reinforcement by using this table. Because it is smallest area, it is small area. Now let's come to the minimum reinforcement required for the steam, which is 12. As the greatest area for that, it will be this one. It will be this one. It will be, so we say provides bars with a diameter of 12 at a spacing of 25 millimeter center to center, which gives the area which is closer to this one. It will be equal to this one, 452 millimeters square per meter. This is the area of distribution steel reinforcement. Now, the next we are required to check for shear reinforcement. The aim to check for shear reinforcement is to check whether the shear reinforcement, which is links, does it required for the design of steam wall? Now, check for shear reinforcement is checked as follows. Check for shear. This is required for this step. Now, check for shear. First of all, is to determine shear stress. Shear stress is determined by taking maximum shear force over BD. Now, maximum shear stress is obtained by taking maximum shear force over BD. Maximum shear force was this one. 73.28 was kilonewton. So to make it in Newton, we multiply by power 3 over BD. B, which is 1000 times effective depth, which is 254. It will be equal to 73.28 exponent 3 divided by 1000 times 254. It will be equal to 0.29. This is Newton per millimeter square. Next, it determine concrete shear stress. Concrete shear stress is determined by taking 0.79 100 times the area of main reinforcements required over BD power 1/3 times 400 over effective depth power 1/4 times SU over